Today, we're diving into something that sounds like it's straight out of science fiction. We're talking about a new way to see the invisible quantum world, a mathematical tool that can literally feel the ground shake just before something impossible is about to happen. Let's explore this quantum seismograph.
So let's start with a question that just messes with your head. In our everyday world, if you throw a ball at a wall, it bounces back. Simple, right? But what if it didn't? What if, in the bizarre world of quantum mechanics, that ball could sometimes just show up on the other side?
But this isn't some kind of magic trick. It's a very real, very measurable phenomenon called quantum tunneling. And it's not just happening in some far-off microscopic system you'll never see.
Yeah, you heard that right. We're not just talking about tiny particles anymore. Thanks to incredible experiments with things like superconducting circuits, we've actually seen this spooky quantum behavior in systems big enough to hold in your hand. We're talking about human-made objects acting like ghosts.
So let's call this our ghost through the wall problem. This strange quantum tunneling is the mystery we're trying to solve.
And we have to solve it because this isn't just some academic puzzle. Being able to predict and control tunneling is absolutely critical for building things like quantum computers. In fact, unwanted tunneling is one of the main reasons that qubits, the building blocks of quantum computers, make errors and lose their information. It's a huge deal.
But here's the catch. Here's the big problem. For everything we know about tunneling, we've had this massive blind spot. We know it happens, but predicting the exact moment a system even gains the ability to tunnel, that's been almost impossible. Think about it this way. Most of the things we measure in physics, like energy levels, they tend to change smoothly, gradually. But those smooth measurements completely miss the hidden, abrupt event, that sudden flick of a switch that makes tunneling possible. It's like trying to predict an earthquake by just watching the clouds. You're using the wrong tool.
So to crack this, researchers realized they needed a totally new perspective. Actually, they needed two different ways of looking at the exact same quantum system.
Okay, so the first way is the classic method, known mathematically as Fisher information. You can think of this as the local view. It's obsessed with all the tiny, fine-grained details, the roughness of the system. It's like getting on your hands and knees and looking at every single grain of sand in a sandcastle. The problem is, this roughness just tends to smooth out and fade away over time. But then there's the new tool, Spectral Torsion. And this is the global view. It does the complete opposite. It ignores all the tiny little details and instead measures the system's fundamental shape, its topology. It's like stepping back and seeing the whole sandcastle. You're not worried about the individual grains anymore. You're seeing the shape of the towers and the walls. And this table just lays out the difference perfectly. Fisher information, the local view, cares about all the high-frequency details, and it just decays smoothly. But spectral torsion, the global view, cares about the overall shape. And look at its behavior. This is the crucial part. It stays constant, and then it jumps. And that jump, well, that's the whole secret. That's the breakthrough. By tracking this spectral torsion, researchers realized they'd basically built a quantum seismographer, a tool that can feel the hidden tremors right before the ground breaks.
All right, so let's walk through this. Imagine you're tweaking a quantum system. As you do, that local view, the Fisher information, starts to change. It just kind of fizzles out. You can see it here, just smoothly decaying away. From this perspective, nothing all that dramatic is really happening. But at the exact same time, our global view, that spectral torsion, is doing something completely different. It's not budging at all.
I mean, just look at that. While all those little local details are shifting and smoothing out, the fundamental structure of the system is rock solid. It's holding steady, completely unchanged.
It holds steady right up until the exact critical moment the system undergoes a topological change, a point where its very structure is about to reconfigure. And at that precise instant, boom, it breaks. That is not a smooth decay. It is a sharp, sudden, discontinuous jump. That is the earthquake on our quantum seismograph. And that quake is the exact signal we were looking for. It's like a giant flare going off, telling us that a hidden pathway for quantum tunneling has just blinked into existence. And that pathway has a pretty cool name. It's called an instanton. The torsion jump doesn't just tell you that tunneling is now possible. It signals the literal birth of the secret passage that allows a particle to get from one side of that barrier to the other. So you might be thinking, okay, that's a neat trick, but this is so much more than that.
Having a reliable detector for these instanton events is a genuine game changer across a huge range of science and technology. This gives us a whole new toolkit. For quantum technology, it means we can finally detect the start of those tunneling errors that plague qubits. For material science, it could help us design completely new quantum materials from scratch. It even gives us a new way to spot hidden phase transitions in all sorts of complex systems. The list just goes on.
And here's the kicker. This is the part that just blows my mind. Trying to detect these events with the old school methods is computationally impossible for any system that's even slightly complex. This new spectral method, though, it's faster. How much faster? By a factor of 10 to the power of 198. That's a number so big it's hard to even write down. This isn't just an improvement, it's a leap from can't be done to now we can.
And that brings us to one last, absolutely wild thought that the researchers themselves put out there. If this tool is so good at detecting fundamental topological changes in quantum systems, could a future version of it one day be used to detect the most fundamental changes of all? Could it spot shifts in the topology of spacetime itself? A seismograph for the very fabric of reality. Now that's something to think about.